and she's going to talk about the strange case of magnetic field-sensitive charge density waves. It's over here. Okay, so
Yes.
please.
Okay. Wow, this is loud. It's fine? Okay. I was a little nervous about giving a talk in the afternoon because I was afraid everybody was going to be in a zombie state. So I'm prepared to do a tap dance or something to wake you up if needed. Yes. But, well, let's see. If I shout loud enough, maybe you'll wake up anyway. Okay, so I'm going to be talking about another uranium-based compound. And so before I start, let me actually thank the people who did the work that I'm about to present today. Two people were most, oops. Where is the pointer? Oh, I see it. So the two people that were most responsible for the work I'm about to show you are Lin Zhao, my former postdoc who did the first part of the work in this presentation, and then Anuva Aishwarya, my former student who did the second part of the work. With the help of these students and postdocs here, we also had a whole bunch of theory help from Ziqiang Wang at Boston College, Manfred Siegrist at ETH, Eduardo Fradkin and Julian Mayman at UIUC. This work would not have been possible without really beautiful single crystals grown initially by Sheng Ran, who was a postdoc in Nick Butch and John Pierre Paglioni's group. And now recently we've been getting single crystals grown by Shanta Saha. Okay, so this material I'm going to talk about today is a real star, mainly because it combines a lot of interesting physics into one system. So the first thing it combines is strong correlations. Sorry, I'm going to keep doing this, I think. I'm not used to this pointer. So it's actually a condo, meaning it's a heavy fermion metal. So that's already interesting. The second thing is there is plenty of evidence now, I think, to show that it's actually a triplet superconductor, which I'll tell you why is interesting by itself. And finally, there is evidence for non-trivial, well, there's evidence for boundary modes. And so far, the jury is out on whether or not these boundary modes imply any non-trivial topology. And I'll be talking about this. So the star of the show is uranium ditelluride, and that's the material I'm going to be talking about today. And the experimental probe that we use is scanning tunneling microscopy. And I'm really grateful to Herman for introducing STM this morning, and also to Andrea for talking about uranium-based compounds. So I think I really can skip over a lot of preamble. Okay. Why are we interested in triplet superconductors? And just this is my two-slide or one-slide motivation for studying triplet superconductivity, and that is through the eyes of topology. So we know that for, let's just go to the topological materials we're most familiar with, which are topological insulators in different dimensions. And we know that depending upon the topology of the bulk, you can have many different kinds of boundary states. For example, if you have a quantum anomalous Hall system, it's a two-dimensional system. And in this material, you can have chiral edge modes, which propagate only in one direction. If you have a quantum spin Hall system, this is another two-dimensional system, you can have helical edge modes, where you have two modes propagating along the boundaries in opposite directions. And if you can also have ordinary, you saw an example from Herman this morning, you can have ordinary surface states or edge states in many materials. And here you have modes propagating in both directions with both spins. But essentially, the topology of the bulk of the material determines what kinds of edge modes you have. And in ordinary topological materials, these edge modes are typically made of electrons, not any exotic quasiparticle. But in a very nice analogy, you can also have similar non-trivial topology in a superconductor. And you have the same kind of bulk boundary correspondence, where the topology of the superconducting states determines what kind of edge modes you have. For example, if you have a 2 plus 1D time reversal breaking superconductor, which is topologically non-trivial, then on the boundary of the system, you expect to have a one-dimensional chiral edge mode. And so on and so forth. For example, in a 3D time reversal invariant topological superconductor, you expect to have surface states. The boundary of the system is the surface. You expect to have two-dimensional surface states, and these would be helical surface states. But the interesting thing about non-trivial topology in a superconductor, and by the way, just like a topological insulator, to get from a topological superconductor to a trivial superconductor, you really have to close and reopen the superconducting gap in this case. Okay, so the interesting thing about a topological superconductor is, first, it's a fundamentally new phase of matter, but second, these edge modes that I've been talking about in a topological superconductor, they're composed of Majorana fermions. So for example, in a chiral topological superconductor, you have these Majorana fermions running around the edges. So where do you find topological superconductivity? A prime candidate is a triplet superconductor. And that's one of the reasons we're interested in triplet superconductivity. There are other reasons as well. Okay. So then the question is, where do you find triplet superconductors? Why, these kinds of pairings can exist. You can have equal spin pairing. We've known this for a long time. It turns out that singlet superconductors are very common. Triplet superconductors have been very rare. People have found them at very low temperatures, under high pressure conditions, and so on. And so it's been very difficult to find triplet superconductors. But we've known for many decades that one place to look for triplet superconductivity is in the vicinity of ferromagnetism. So if you have a ferromagnet or ferromagnetic fluctuations, and then you get superconductivity, then you know that there's a chance that such a material would be a triplet superconductor. So uranium ditelluride actually is one such material, and that's what I'm going to talk about today. Uranium ditelluride has been known for a very long time, for more than 50 years. It was first synthesized as a powder, and as soon as it was made into a single crystal in the early 2000s, it's been known that this is a heavy fermion compound. Okay, and so there's a huge gap between the 2000s and 2018, where superconductivity was discovered, and I think one of the reasons is that the superconducting phase in uranium ditelluride is actually very sensitive to the uranium-tellurium ratio. And so for a long time, the perfectly stoichiometric uranium ditelluride compounds turned out not to be superconducting. And so superconductivity was only discovered very recently by Sheng Ran. Okay, and the moment superconductivity was discovered, they immediately knew actually that there were strong indications that this is actually a triplet superconductor. But before I go into that, let me just talk about the normal phase of this. Oh, yeah, let me talk about crystal growth. So initial compounds were made by a chemical vapor transport. This is what the crystal looks like. This is the unit cell, so you can see it here as well. Just to give you a sense of what the symmetry of the system is, as well as the bands that are close to the Fermi energy. So this is a body-centered orthorhombic material with the IMMM space group. The way you visualize this material is, okay, these red balls here, they are the uranium, and then the green and the whitish ones are tellurium. So you can think of it as a bitrigonal prism of telluriums, these telluriums surrounding a central uranium atom. In each unit cell, there are 2 uranium atoms. So this is what the unit cell looks like. And it actually has these chains, uranium chains, that lie along the A direction. And then it also has tellurium chains that go in a perpendicular direction. But you can see these lines of telluriums also look like chains. So I'm also going to be calling these telluriums tellurium chains. The bands that live close to the Fermi energy are the uranium 6D bands and the tellurium 5P bands. and these are actually hybridized with each other. And so this Fermi surface is not very complicated, but these are the bands that live close to the Fermi energy. Additionally, it's a heavy fermion compound. So of course, there's the F state that at low temperatures also lies close to the Fermi energy. So now let me talk about STM on UTe2. You heard this morning, I don't have to go into it. STM is a very nice probe. The way it works is you bring a tip very close to the sample that you'd like to study. You turn on a small potential difference. Electrons tunnel from the sample to the tip, or to the tip from the tip to the sample, depending upon the direction of this bias voltage. And essentially, the way I think about STM is that it's really a measure of the tunnel current as a function of position and voltage. Okay, that's all you need to know about STM. We measure this tunnel current, and you can measure it as you change the voltage. You can measure it as you change the tip sample distance. You can measure it as you change raster the tip across the sample. In fact, simplistically speaking, a measure of the tunnel current as a function of position gives you the topography, and a measure of the differential conductance, a di/dV. You take IV and you differentiate it. So a measure of di/dV, measuring di/dV gives you the density of states. Okay. So just as an example, if you were to measure di/dV for a simple metal, you should see a straight, flat density of states that goes across the Fermi energy, no big features. If you measure the di/dV for a superconductor, you should see no states at the Fermi energy because we are tunneling in single electrons and all the electrons in the system are paired. So the density of states up to the gap energy will be 0. And then right at the gap energy, you see these strong coherence peaks. Okay. So now let's look at uranium ditelluride. This is the crystal structure. When we look at any material, we don't know a priori whether it's going to cleave or not. And for STM studies, because we are sensitive to the surface, we actually cleave the crystal. There are other methods of preparing surfaces as well. But in this case, we will cleave this material. So the question is, where does it cleave? Let's just look at the topography first. This is what the topography looks like. And as it turns out, this material cleaves along this very interesting direction, which is 0, 1, 1. So it cleaves along this direction. And we know this just by looking at the surface, measuring the distances between the atoms, and looking at the heights of the step edges. Okay. And in the topography, what we are primarily seeing are these tellurium atoms. And we can also see this uranium atom right underneath if we actually filter out these tellurium chains. Okay. So now the normal state of UTe2 is a heavy fermion metal. And how can we see evidence for this from STM? And just very briefly, let me remind you what a heavy fermion metal is. I like to think about it in this way. So in a heavy fermion system, you have these localized moments living on a lattice. And let's say they occupy an F state. Because you have a bunch of F states living on a lattice, you can think of them as forming some kind of a band, which I'm labeling here as an F band. So here's a representative Hamiltonian of the system. You have these localized moments, and surrounding these localized moments are the conduction electrons, which have some kind of a dispersion crossing the Fermi energy. So this is your high temperature view of a heavy fermion system. As you cool down, what happens is the interaction between these localized moments and these conduction bands gets stronger and stronger. And that has two consequences. The first consequence is this F band, which can lie anywhere below the Fermi energy, gets actually pushed up to the Fermi energy due to the strong interactions. And the second consequence is that it creates a hybridization between the F band, which is the flattish band, and your conduction electrons, and that creates a gap. So as you lower temperature, you get into this state, which is called the heavy fermion ground state, where this has happened, the two bands have hybridized, and also the local moments now have been screened by the conduction electrons. And if you look from far away, you won't even know that this system has local moments. So the local moment physics is now really gone. Okay. Now, depending upon where your Fermi energy is, so if the Fermi energy lies in this gap, you have an insulator. So there are heavy fermion insulators. And if the Fermi energy actually lies in one of these up here, then you have a metal. And uranium ditelluride is a heavy fermion metal. Now, the question is, when you do spectroscopy, what should you see? If the Fermi energy is indeed here, what you should see is a sharp peak in the density of states right at the Fermi energy, okay? So now let's do STM spectroscopy and look for the sharp peak in the density of states at the Fermi energy. And this is what the STM spectrum looks like. And by no means is this a sharp peak in the density of state. It has a very strange line shape. It's got a small peak here and a large dip here. And we actually know what this line shape is. This is called a Fano resonance. And it's actually due to a sort of an interference process. It's a result of the tunneling process. So in reality, there's actually a sharp peak in the density of states in the sample. But when you tunnel into this, you can either tunnel into the localized state or the continuum that I said exists. And these two processes can interfere with one another and end up in this very strange line shape called the Fano line shape. In any case, anytime you see a Fano line shape, you should immediately translate into your mind as the existence of a peak in the density of states right there. So this is what the normal state looks like. This line shape is reminiscent of such Fano line shapes in many heavy fermion systems. And by fitting this line shape, you can get many things, including the Kondo coherence temperature, which from our data, we estimate to be 30 Kelvin. And that's what you also see from transport. Okay, superconductivity sets in at 2 Kelvin or 1.6 Kelvin. The Kondo coherence temperature is 30 Kelvin, which means that the superconducting phase in this system is emerging inside. All the Kondo stuff has already happened many decades before, okay? So now in the superconducting phase, you have all of these bands, you have the F bands, and you have the D bands from the uranium, and you have the P bands from the titanium, and these are the players in the superconducting phase. Okay, so now let me show you evidence for the triplet nature of superconductivity. Essentially, there's night shift data, and for a singlet superconductor, if you go below the superconducting transition temperature, you see a huge change in the night shift. Whereas for a triplet superconductor, depending upon the direction of the magnetic field with respect to the D vector, you'll either see no change or a very small change. In uranium ditelluride, we see a very small change. This is not our data. This is this paper. You see a tiny change in all three directions. The fact that the change is very small tells you that it's a triplet superconductor. The fact that you see a small change at all in all three directions tells you that the direction of the D vector doesn't point along any of the principal axes. It's in some other direction. Okay. There's also the fact that Hc2 in this material is extremely high, far above the Pauli limit. So Hc2 actually is close to 15 to 20 Tesla, and in certain directions, it's even much larger than that. Okay, so now knowing that this is a triplet superconductor, let's do STM and look at the superconducting phase of the system. Remember that this this Kondo stuff is happening at high temperatures. So the energy scale of this stuff is about 10 millivolts. Superconductivity is happening at 1.6 Kelvin in the sample that I'm going to show you. That energy scale is less than 1 millivolt. So in order to look for superconductivity, we have to look right here, okay? So now let's look there. This is a plus minus 1 millivolt spectrum. And if you take a line cut, you see an extremely strange looking shallow superconducting gap that has no coherence peaks. And you don't know that this is actually a superconducting gap. So we can do temperature dependence and the gap goes away at the right temperature. We can do magnetic field dependence and the gap disappears close to the Hc2. It's almost gone. At 10 Tesla, that's our largest field. And that's 11 Tesla or 12 Tesla is the Hc2 in this direction. So based on the suppression with temperature and magnetic field, this very, very shallow gap is the superconducting gap in this system. This has been confirmed by other groups as well. Just to tell you how shallow it is, shown here in red is the superconducting gap that we measure on UTe2. And this is another material, molybdenum tellurium selenide. This is the spectrum for that. You can see it's got almost the same TC, but you can see nice coherence peaks, and the gap goes pretty low. Okay, so the shallowness of the gap in UTe2 is actually a big mystery. Okay, so the first question we can ask is, does UTe2 have boundary states? What do the boundary states look like? Remember, I said at the beginning, if the material is topologically non-trivial, in fact, superconductivity is topologically non-trivial, what you expect is states inside the superconducting gap at the boundary of the system. So one boundary is a step edge. So let me just show you what data look like along a step edge. So this is a line cut obtained from this is a step edge. Far from the step edge, this is spectrum 1, you can see the superconducting gap. And as you go close to the step edge, you can see that there's extra density of states that emerges inside the superconducting gap. But this happens only on one side of the Fermi energy, not on the other side, okay? Now, if you look at two step edges, which are in opposite directions, you find that this extra density of states appears on the opposite sides of the Fermi energy along these two step edges. So this is the first observation. And so basically you have density of states inside the superconducting gap that emerges along the step edge. It's got this very funny character where it happens on only one side of the Fermi energy or other side of the Fermi energy. And we don't actually understand what's going on here. So one question is, does this have anything to do with superconductivity? And the answer is yes, it does, because these bound states, let me just go ahead. These bound states disappear at TC, and they also disappear at HC2. So this is magnetic field dependence. These are the bound states. At around 10 Tesla, the bound states are gone. So based upon these two things, I can tell you that we have very interesting looking bound states at the step edges in UTe2. We don't understand the line shape of these bound states. And in fact, if you look at a 45-degree step edge, you also see a bound state inside the superconducting gap. This one lives right at the Fermi energy. Okay, so actually I don't have time to talk about these bound states, because today what I really want to tell you about is the observation of an extremely interesting charge density wave in this system. Let me just leave you with this one thing about these bound states. We actually don't know what these bound states represent. We don't understand their line shape. We don't know what these imply for the topological properties of the superconductor of superconductivity in UTe2. We really don't understand these bound states. With that, let me just move on. Okay, how much time do I have? I have 5. Oh, okay. 10 plus 5, right? Because I started at 45. In fact, after 45. Okay, just saying. I'm just saying. I looked at the word just for this. Okay. 10 plus 10. Okay. No. I started even after 45. Okay. All right. Let me just now talk about what other surprises might there be. So I've shown you topography. This is what the topography looks like. And just very quickly, this is the three-dimensional Brillouin zone. This is the cleave plane, and the surface projected Brillouin zone looks like this. Okay, just so you know what it looks like. Okay, now if you take a Fourier transform of the topography, you see the Bragg peaks. They are these. These are the Bragg peaks here, and they correspond to this unit cell. Okay. In addition to the Bragg peaks, inside these Bragg peaks, you have 3 additional peaks here, 1, 2, 3. And the question is, what are these 3 additional peaks? And now in STM, when you start seeing additional peaks, they could be due to something called quasi-particle interference. but it could also be due to a charge density wave. So the question is what are these three peaks? Let's just look at them in real space first. So this is topography. This is a DIDV map at 6 millivolts. And you can see that this looks very different from the topography. So here's the topography again. Here's the DIDV map. You can see stripe-like features going in this direction. These correspond to this peak right here, because this peak has the right periodicity and the right direction. In addition, you can also see dots. They almost skip each. They're at a period of almost 2, right? These dots correspond to these 2. So you have these features in the density of states maps that correspond with these features in the Fourier transform. And the question is, what is this? And you can ask, is it a charge density wave? In STM, one sort of evidence that something is a charge density wave is that its Q doesn't change with energy. So you can plot the energy versus the momentum position of each of these Q vectors, and you can see that they don't change. And based on this, we can actually say that this is most likely to be a charge density wave. Okay. All right. So there is this this charge density wave. You can yes. Topography. But from these are DIDV maps. Yeah. This is, I can't remember what it is. Yeah. The second thing is that these CDW peaks occur at incommensurate Q vectors. Okay, just the direction is not in the direction of the Bragg peaks. That tells you that it's incommensurate. Okay, so the important thing that I want to show you today is that the CDWs respond in a very strange way to a magnetic field. So this is the 0 Tesla Fourier transform. You see these 3 CDW peaks. This is the same 3D kind of rendering that Philip was showing you this morning for the Kagome systems. You can see this tall one here is this one, and then these 2 on the side are these 2. Now let's turn on a magnetic field, and what you find is, first, all 3 peaks are suppressed. This one, and this one. They're all suppressed. You can even compare these 2. The second thing is that one of this is much more suppressed than this, and it's actually, this one is almost completely gone. This is not a huge surprise because the suppression of this charge density wave is a huge surprise, because that's not expected for a normal charge density wave. But that one is suppressed more than the other is not surprising, because a magnetic field breaks mirror symmetry in any case. Okay. Now we got really lucky, as it turns out that this sample, the HC2, is extremely sensitive to direction. So if we can change the direction of a magnetic field a little bit, then we can realize the HC2 in the system. So in fact, we managed to get samples which were 11 degrees off. And at this angle, HC2 is about 10 Tesla. So now when we apply a magnetic field, what we find is that at the HC2 of the superconductor, this charge density wave is completely gone. So what I'm plotting here is the charge density wave intensity of the 3 charge density wave peaks, 1, 2, 3, as a function of magnetic field. So you can see all of these peaks are fully suppressed by 10 Tesla. So here we have a charge density wave that disappears with magnetic field close to the HC2 of the superconductor. And the question is, what could this be? Why do you have a CDW that disappears at HC2? So one possibility, this was suggested by our collaborators, Eduardo Fradkin and his student, Julian Meyman, is that you actually have a pair density wave in this system. So the idea is, this is a Ginzburg-Landau theory of a uniform triplet superconductor and a triplet pair density wave order. And if you write down all the possible terms that you can have, you can show that in this scenario where you have a uniform superconductivity plus a PDW, you will get a charge density wave. And this kind of a charge density, this triplet pair density wave state, explains the magnetic field sensitivity, because when you turn on a magnetic field, you get vortices, and these vortices suppress both the uniform component as well as the pair density wave. And when both of them disappear, the charge density wave also disappears. And so the question is there any other proof that this is indeed happening? And this is the last part of my talk. So the same theory also indicates the following. When you turn on a magnetic field, you should have vortices of the superconducting order parameter, and you should have half vortices of the pair density wave. Theory indicates that when you have half vortices of the pair density wave, that should induce dislocations, which is a phase winding of the charge density wave. So what you really should be looking for is areas of your sample where the charge density wave order parameter also winds, and these point dislocations, the density of these point dislocations should increase with increasing magnetic field. So the question is, can we see these point dislocations where the phase of the order parameter actually, this is not superconducting, remember, this is the charge density wave order parameter winds by 2 pi. And do these increase as you increase magnetic field? And does this have anything to do with the mechanism by which the charge density wave disappears as a function of magnetic field? So in the next few slides, that's what I'm going to show you. So what we can do is, fortunately, we have access to all of this through the Fourier transform. So what we can do is we can take a Fourier transform, and by looking at the charge density wave peaks, we can extract the following information. We can extract the amplitude of the CDW order parameter. We can extract this cosine QR, which is the oscillatory part of the charge density wave, plus any phase slips. If there are phase slips, we'll extract that as well. And finally, from this map, we can also extract the relative phase. And the relative phase should show you any positions, any point dislocations in this field of view. So just as an example, so this is actual real data. This is the amplitude. This is the CDW in one direction. These are positions where you have a phase slip. Now let's look at just one of these. Just focus on this one. We can plot the phase as a function of position. And for this one, I mean, as you go around this dislocation, and you can see that the phase winds by 2 pi in the spiral fashion. This is data, by the way. This is not theory. Around this particular dislocation. Similarly, pick another dislocation right here. You can see the phase is now winding in the opposite direction by 2 pi. And if you go far away from a dislocation, then the phase just doesn't change at all. Okay? Now we can look at what happens in a magnetic field. So this is a series of inverse Fourier transforms of one of the 3 components of the CDW with increasing field. You can see with your eye that the number of point dislocations is increasing as you increase field. And you can see in this relative phase map that the number of these phase windings is increasing. Interestingly, the colors here represent the direction of the winding. And you can see that these phase windings come in pairs. So you have these pairs of dislocations with opposite phase windings that increase with increasing magnetic field. And the last question you ask is then, do these dislocations actually kill your charge density wave order? And to do that, what you can do is you can actually look at the amplitude map, and I'm sort of running out of time. Look at the amplitude map and compare that with this map of the dislocations, and there's a direct one-to-one correspondence between the positions where the amplitude goes to 0, that's these positions. These are all positions where the amplitude goes to 0, this amplitude of the CDW order parameter, and the locations of the dislocations. So essentially, what our analysis is saying is the following. When you turn on a magnetic field, you have vortices in both the uniform superconductivity as well as the pair density wave. These pair density wave vortices are actually half vortices. Each half vortex generates a dislocation in the charge density wave, because as the phase of the PDW winds, so does the phase of they're intertwined orders. So as the phase of the PDW winds, so does the phase of the charge density wave. We can see that this is happening in real space. As you increase magnetic field, you're generating more and more of these point dislocations. By the way, these are topological defects, these point dislocations. You're generating more and more of these topological defects. They come in pairs with opposite winding. Their numbers grow. At the position of each such dislocation, the amplitude of the CDW order parameter goes to 0. And this is how the charge density wave gets killed with a magnetic field. And this is predicted by the Ginzburg-Landau theory. And anyway, this is the summary. Thank you for your attention.
Thank you. Now it's audience time.
Okay.
How much time is there like?
Really? Okay.
Just be prepared to
That's
answer.
very generous.